Okay, deep breath. Final exams are right around the corner, and I know the pressure's on. If you're cramming for that chemistry test, you've come to the right place. We're gonna make this painless. Welcome to the Explainer, your secret weapon for absolutely crushing the states of matter.
So yeah, let's just cut right to it. We're going to skip the fluff, focus on what you really need to know, and most importantly, point out those tricky questions where students always lose points. Stick with me and you're going to be ready. Everything, and I mean everything, starts with this one big idea, the kinetic molecular theory. Seriously, just picture it in your head. Everything around you, the chair you're sitting on, the water in your glass, the air, it's all made of these teeny tiny little bouncing balls. And the key thing to remember is they are always moving.
Okay, but what does that bouncing ball idea actually look like? Well, to make sense of it, let's ditch the textbook and head into the kitchen. Trust me, this simple pot of water on a stove is going to make it all click.
Think about it. You grab some ice from the freezer. It's a solid, right? Those little water molecules are bouncing balls. They're all locked together in a super organized pattern. They're moving, but they're just kind of vibrating in place. Now you throw it in the pot and turn on the heat. You're pumping in energy. That energy lets the molecules break loose and start sliding past each other. Boom, that's liquid water. Crank that heat all the way up to a boil, and you give them so much energy they just completely break free and start flying all over the place. That's steam. That's your gas.
And that right there is the big secret. When we talk about temperature, all we're really talking about is how fast those little molecules are zipping around. High temperature means fast-moving molecules. Low temperature means they're slow and sluggish. It's really that simple.
So check this out. What happens when all those speedy molecules are trapped inside a container? Well, the harder you make them, the faster they move, right? And the faster they move, the more often they slam into the walls of that container. More slams mean more force, which means higher pressure. It's a direct relationship, and you can bet you'll see a question about this.
Okay, lightning round review. Solids, they have a definite shape and volume because their molecules are stuck in place. Liquids, they'll take the shape of their container, but they still have a definite volume. And gases, total rebels. They take the shape and the volume of whatever you put them in. And check out compressibility. You can't really squash a solid or a liquid, but a gas, all that empty space between molecules means you can totally compress it.
All right, now for the really good stuff. This is the insider info. We're diving into the tricky questions, the concepts that are designed to trip you up. This is what separates a good score from a great score, so pay close attention.
First up, this is a classic mix-up. Diffusion and effusion. They sound similar, they're both about how gases move around, but they are not the same thing. Be honest, could you explain the difference with confidence right now? If not, you're about to.
Here's the teacher's shortcut you need to burn into your brain. Diffusion is about mixing. Think about spraying perfume. Those molecules spread out through the air molecules until the whole room smells it. Effusion is about escaping. Think of a tiny hole in a tire. The air molecules are escaping through that one little opening. One is mixing, the other is escaping. That's it.
And here's the one rule that applies to both of them, and it's called Graham's law. It's super simple. Lighter molecules are like little speed demons. They will diffuse and effuse way, way faster than big, heavy, sluggish molecules. So if a question asks you to compare helium and, say, argon, you know right away that tiny little helium is going to be moving much faster.
Okay, next exam trap, allotropy. The easiest way to think about this is like an element having a major identity crisis. It's the exact same element, same number of protons and all that, but depending on how its atoms are arranged, it can show up as completely different things with totally different properties.
And the poster child for this, the example you are almost guaranteed to see on your test, is carbon. It's just carbon atoms, but boy, can it have two very, very different personalities.
So on one hand, you've got diamond. In a diamond, every carbon atom is locked into this super strong, rigid 3D network with 4 other carbons. That structure is what makes it one of the hardest things in the world. But then you've got graphite, you know, the stuff in your pencil? It's the same carbon atoms, but now they're arranged in these flat sheets that are just kind of stacked on top of each other. They're not strongly connected, which is why graphite is so soft and slippery. Those layers just slide right off onto your paper. Same element, totally different arrangement, totally different properties. That's allotropy. Okay, you've got the basics down, you know the common traps. Now, if you want that A+, if you want to show you really know your stuff, you got to know what happens at the very, very extremes. We always talk about solid, liquid, gas, but what's beyond gas?
Well, if you keep adding energy, like insane amounts of energy, like you'd find on the sun, you get plasma. It's a superheated gas where the atoms get ripped apart into a soup of electrons and ions. That's the fourth state. But what if you go the other way? What if you get things colder than cold, down to almost absolute zero where all motion is supposed to stop? You get the fifth state, a Bose-Einstein Condensate. It's wild. The atoms get so cold and still, they kind of lose their individual identities and merge into one single superatom.
Whew, okay, that was a lot, and we went through it fast. So how do we make sure it all sticks for the exam? I've got one last thing for you, a super simple memory hack to tie it all together.
At the end of the day, the 5 states of matter are just a story about energy. Just think of it like a temperature scale. At the absolute rock bottom, the coldest you can get, you have Bose-Einstein condensate. Add a little energy, it becomes a solid. Add more energy, you get a liquid. Keep going, you get a gas. And at the very top, with a ton of energy, you have plasma. BEC, solid, liquid, gas, plasma. You're just walking up the energy ladder.
And I'll just leave you with this one last question to think about. We talked about carbon's identity crisis, how it can be both diamond and graphite. So what other elements out there do you think have their own secret identities, their own allotropes? It's a cool thing to think about. All right, that's it. Go crush that final. You've totally got this.